Okay, so this numerical approach, yeah. All right, so the numerical approach to the Schrodinger equation and the transition dipole moment integrals is something that I took the analytical calculus results and I took the group theory, and that was that book that I wrote. That was the spectroscopy theory. I thought, 10 years ago, I thought, the integral is just a sum. And in Excel, if you just sum a column and multiply by the x increment, you've taken the integral. Would that work? And so I just put up the wave function and I multiplied by itself, wave function times wave function, psi squared, and integrated that and multiplied by the x dx, and I got 1. So it was normalized. Integration is easy in Excel. It's a sum. All of the crazy substitutions and integration by parts and all of that stuff that you did for the analytical calculus, all you need in Excel is the sum, because that's what an integral is. Doesn't matter how complicated the function is, or if you've got 3 functions times each other and so on. And so then I tried the orthogonality. I took a wave function times a different wave function and did the sum, and it was 0. And then I tried the second derivative. I took the wave function and the first derivative, the second derivative, which is, again, just rise over run. In the table, it's real easy to do. This value minus that value divided by the x value minus the other x value. The rise over the run gives me the derivative. So I took the derivative of the wave function and got the second derivative of the wave function, and then multiplied the wave function times its second derivative, and I got the Schrodinger equation, energies out of it. So that's what we're talking about with this numerical approaches. So I'm going to leave, obviously I'm going to put this video up. I'm going to leave last year's video up. So you have at least 2 versions of the same material if you want to watch them both. You're not going to find this on YouTube except for my channel for the things. So you probably have 3 versions of this, but the last 2 are the most applicable to your exam. And so the homework is also sort of screenshots of this spreadsheet that are in this video, screenshots of the spreadsheet you're going to be working with next week in lab. And it's just to make you go into that spreadsheet and to know what you're doing. Because this is can be a very cookbook operation. If you're reading through next week's lab and it tells you to plot this function and do that, and you're just following directions, but you're not engaging the mind, you don't really see the quantum mechanics behind it. You're just going through the motions and getting the same little curves, but you don't. So I want to ask you questions about those curves and those wave functions to see if you understand what you're seeing. And that's what this homework is about. That's what the exam is about. So let's jump into this numerical approaches to the Schrodinger equation. Jacqueline, can I get you to close that door for me, please? So why use numerical methods of calculus? Well, remember Dirac in his paper, he said that the underlying laws of math and chemistry pretty much are completely known, but that these equations are much too complicated to be solvable. What does that mean? It means there's no analytical solutions, but we can take the sum of any function no matter how complex it is. So we use numerical methods to solve these equations. They're not exact integrals. We don't get an analytical result. We get a numerical result. We get a number with decimal places, but it doesn't tell us what part of that number is mass, what part of that number is L squared. The analytical result we got had L squared in it, had delta n, had n. It had all our variables in it. You lose that when you go to numerical methods. So you don't, of that number that you get at the end, you don't know what part of it is related to L, or what part of it is related to n, or delta n, or m. You can only get those kinds of things from the analytical method, okay? But you do get the result. And so then you can change L, and you can see how the result depends upon L. And you're like, oh, it depends upon L squared, or some kind of complicated, dependence. Anyway, so numerical methods are very visual. Analytical calculus is not very visual. It's just math on the page. Okay, now mathematicians are mathematicians because it's visual to them. Right? They look at those equations and they see what's going on. I never really saw what was going on I'm still working on that. As I get more into PChem and saw how it was applied, I kind of could see, okay, this is the wave function and the overlap and everything, but it's a skill. It's an acquired skill. But you go into the spreadsheet and you have a wave function, you can plot it and you see the wave function. And you can see where it's 0 and where it's not and so on. So I like this because it's very visual. And again, analytical solutions only exist for very few systems. Any single electron system, particle in a box, particle in a ring, a hydrogenic atom, which only has one electron, and the H2 plus molecule, which only has one electron. And it's because the wave functions, the electrons are described by wave functions. And so where's the location of that electron? It's hard to do the Coulombic repulsion and attraction when the particle's not in an x, y, z coordinate. When it's spread out on a wave function, there's no way to handle that mathematically. And so there's no way to solve these multi-electron problems analytically. And the numerical methods use fast computation of complex problems. So what would take you, quite a while to do by hand, we can put it in a computer and get the result. And you'll see that today. I give you a low resolution spreadsheet so you can see everything on the screen, but I have a high resolution spreadsheet that has like 200 divisions of the box, where y'all will have 11 or 10 divisions. And on mine, I take 15 wave functions times 15 more wave functions. That's 225 integrals. And the time it takes me to do 225 integrals is Control-Shift-Enter. Right, and it does them. So you can't do that many transition dipole moment integrals by hand, with Control-Shift-Enter. So this is what your spreadsheet will look like next week in the lab. Now your spreadsheet has all of these little tasks up here: task 1, task 2, task 3. So follow these in order. So just follow these little breadcrumbs. I'm telling you exactly what I want you to do, when I want you to do it. So do everything in that order. Down here, yours is blank. So the wave functions are not entered for you. Okay, so here's your wave function equation. And I want you to take this equation and I want you to enter it into here. So that equation goes right in there. And that's where you're going to use anchoring. So if you haven't done the Excel Bootcamp lab, you need to, go back and learn about anchoring. So this wave function is going to refer to the x-axis. So that's x. This x is right there in that axis. It's going to refer to the quantum number. So it's going to point up to that quantum number. And you're going to anchor the row, but not the column. So that when you copy that wave function over one, it's now referring to the quantum number above it. So when you anchor the row, you can copy it down and it still looks at that row. But when you copy it over, it moves with the wave function. So be smart with your anchoring. When you're anchoring cells, you can use F4 to go through anchoring both, anchoring the row, anchoring the column, taking away all anchors. You hit it again, it goes back to all four. So you just hit F4 until you get the percent sign or the dollar sign in front of either the row or the column. And so then, and then L. So this L will be anchored all the way up here. Here's L. And then the quantum number is anchored above, and that's it. You anchor L, you anchor the quantum number. In Excel, you can type in pi, open, close, parenthesis, and that gives you pi to, I don't know how many decimal places. So whenever there's a pi, just put times pi, open, close, and it's a function that returns pi. So you don't have to type in 3.14159, etc. And so that's your two wave functions. And then you can plot them. So one of these is, task 2, plot the wave functions. So then you make your little graph. You plot these two wave functions. Use lines, no markers. And here we have, and the nice thing about this is then you can play with it. So you can come in here and you can make that wave function 1, wave function 2, wave function 3, and you can see how they change on the plots. That's the very visual part. So have fun with your spreadsheet, okay? This is the part where you're learning Excel and you're like, oh my gosh. But this is the most transferable skill you come out of this class with. And years ago, I had a student call me and he said, I got a raise, on the spot raise. And I said, really, what happened? He said, my boss gave me some data and he said, do you know how to plot data? So he said, I pulled it up in Excel, made a beautiful little plot, put, title on the chart, titles on the axes, put the units on there, and just like PChem. And I handed it to him, and he looked at me and he goes, I'm not paying you enough. You're going to get stolen by another division. So he gave him a raise. Your results may vary, as they say online, but still, it's one of the most transferable skills, which is why I chose to use Excel, not MATLAB. So there are more powerful math programs that can do this visually and show you all these things. It may even be easier to use, but you may not always have MATLAB wherever you go, but you'll always have access to Excel or some other kind of spreadsheet. I mean, even Google Sheets, you could do this in Google Sheets. There's a few things that Google Sheets doesn't have that Excel has, but it's pretty small differences. Once you make the wave functions, then you can play around with it. Task 3 is let's compute the products. And so wave function squared. So this is just psi n squared. So it's just that number squared. And you copy that down. And you can plot those. And so here, this blue one is psi, and it's got a little, quantum number 2 there, squared. And so that's this blue one squared. You see how it's squared. The positive region is positive. The negative region has become positive. And then if I integrate this overall space, right, the sum of wave function squared times dx. Where's dx? Dx is right here. So anytime you do your integrals or your matrix multiplications and so on, you've got to multiply by dx, or you're not getting the area under the curve. You're just getting the vertical lines. So what is this integration? Notice I'm taking the height of these are the heights of the curve. So this is the vertical distance of the curve. Dx is the horizontal increment. And so integration is just these boxes. I'm taking these boxes. That's the height times dx, right? dx. The height times dx. So I'm taking all of these columns, these little boxes, and I'm adding them up. This one is actually 0. Okay. Did you see what's going on with the integration? It's just that height times dx. I'm getting a bunch of rectangles and adding them together. So this is the integral. You see that? That's all it is. The heights of every data point in that curve times dx added together. It's the area under the curve. Is it accurate though? What changes the accuracy? And this is, if you're kind of drowsy this morning, wake up right now. Okay. Yeah.
Is it the number of boxes you put underneath the?
Yeah. So look at the error, right? Is this triangle right here under the curve? No, it's not. And this triangle is not under the curve. Those triangles are huge because my dx is huge. If I made a bunch of smaller dx's, dx was much smaller, I'd have a more accurate integral, okay? And I will say this is not very fine. Fine is the term for that. Not very fine, therefore not accurate. But it's close. And we'll see in a minute, it's about 12% off. Okay. So if you wanted to make a numerical simulation, you can write this down as sort of on the side. If you want a numerical simulation to be accurate, you need a fine grid. You need a very small dx. Do you understand why? Yeah, good. I see nods. Okay. Now, if I take this wave function times the other wave function, right? I've got psi of n times psi of n prime right here. That's the orthogonality piece, right? A wave function times a different wave function added together times dx is 0. Okay. Now, I wanted you to get some skills with different formulas. And so in the notes, we'll see in a second this sum product formula. So you can just type in, like right here, this was the sum of this, actually it was the sum of this column right here. So the sum of that column right there. This was the sum of that column. But notice to do wave function squared, I had to make a new column. Or to do wave function 1 times wave function 2, I had to make a new column. You really don't have to. This sum product right here can just be equals sum product, open parenthesis, and then you just select this column here. Okay, that goes there in a selection, and it'll put the little references for that column, comma, and then you select that column again. We're doing psi squared, and we do it twice. That column, comma, that column again, and it takes every data point in that column and multiplies it by the data point in the other column, and then adds it together. So it is doing what we did with this column here without making a new column. It's just a way to take two arrays, multiply them by each other, and add them up. Times dx, you get an integral. Okay. And then we'll talk about this matrix multiplication in just a second. So let's dive a little deeper. So let's talk about arrays. And we'll do all these different types of things. Arrays of numbers, array manipulation, matrix multiplication, and so on is our ultimate goal. And then numerical integration. So any row or column or block of numbers is an array. So in Excel, we see these columns of numbers. Those are arrays. And so you could have a row of numbers, or you could have a column of numbers. And so we use matrices. These are just sort of one-dimensional matrices. You refer them by row by column. So this is a 1 by 3. This one's a 1 by 3. And this is a 3 by 1. So it's row first, column second. I always have to look that up, so I never can remember it. So keep these notes. So what about array manipulation? Let's learn by inspection. So if we transpose ABC, we flip it from a row to a column. And we turn it on that top left number. So that ends up being what we call the diagonal. If we transpose a column, we can flip it into a row. It's not exactly clear that that's a diagonal because it's just a single number. So let's look at this one. So A, B, C, D, E, F in this matrix. If we transpose that, then notice how AE makes a diagonal. And they stay in the same position. You know, first row, first column, second row, second column. They stay, and everything else flips around them. So in Excel, we do this by transpose array. Now, notice these curly brackets. These are important, okay? You don't have to type these in. What you do is you select where you're going. So you would select these 6 cells with the mouse, okay? And then you start typing, and you type this piece right here. You type this into here. So step 1, select array, result. Result spot. Okay. So that's where I want the array to go, like the final result. And then type formula. So that's step 2. And step 3 is hit Control plus Shift plus Enter. So you've got all this selected, you type in a formula. So you're typing a formula into 6 cells at once. And how does Excel know you're doing that for 6 cells? The Control-Shift-Enter is what you get. If you don't hit Control-Shift-Enter, Excel will say, hey, you're trying to enter an array formula. And to do that, you need to hit Control-Shift-Enter. So it'll give you a prompt. And so, so you type this formula, but you select this array here. You select that. So instead of typing the word array, you select the cells that you want to transpose. Okay, so you select where it's going to go, type in equal transpose, open parenthesis, then you select the thing that you're transposing, close parenthesis, control shift enter, boom, you've got it. So that's how you enter an array formula in Excel. Now let's do array multiplication. So if we take 1, 2, 3 as a row vector or a row matrix, and we multiply it by a column matrix that's also 3 rows, then this is what we end up with. It's the first cell here. It sort of tips up on its side and sweeps through this. So 1 is multiplied by A, 2 is multiplied by B, and 3 is multiplied by C, and they're added together. So this is an integral. It's also sum product. So what we did with sum product, we could do with array multiplication. In Excel, sum product array 1 and array 2. So we could select those and hit enter, or we could also use mmult. So this is matrix multiplication. It's just an expanded form of the sum product function. So if we have this 2 by 3 matrix and multiply it by this 3 by 2 matrix, this is what we end up with. So this is the first row. So R1, and this is the first column, C1, and so the result of this will go in row 1, C1 of the result. So if we look at our matrix, this is row 1, C1. Do you see how that worked? The first row times the first column gives us a number in row 1, column 1 of the result. This sweeps through when it hits column 2. It gives us this one. So you see the 1, 2, 3. So this is row 1, C2. And it came from multiplying row 1 times C2, column 2, and adding all that together, and I get this value. So this is how we take all of these possible rows and multiply them by all of these possible columns, because then we get the second row, R2 times C1, then we get R2 C1 down here. And then R2 times C2, we get R2 C2. So we have 4 integrals here that we've done with Control-Shift-Enter. I've got 2 arrays here and 2 arrays there. I do this matrix multiplication, and I get 4 integrals out of it. I get all possible combinations. So in Excel, this is using the mmult, which is matrix multiplication. Very, very straightforward. I select the result, which is going to be a 4 by 4 matrix. Then I start typing the formula. Then I select array 1, I select array 2, and then close parenthesis, Control-Shift-Enter, and it fills those 4 cells with the 4 integrals. So that's what we have in that spreadsheet down here. I'm going to scoot back just a little bit. Right here. So right there is the 4 integrals of this wave function n and wave function n prime. So I took these guys, I transposed them, and then I put them in mmult with these 2 columns untransposed or not transposed, hit Control-Shift-Enter, and I got 1, 0, 0, 1. Those are the integrals of those 4 wave functions, of those 2 wave functions in all combinations. So let's go back to look at the matrix multiplication rules, because there are some restrictions on multiplying matrices. So if I have matrix 1 times matrix 2 giving matrix 3, I have to have those middle numbers match. The columns on the first matrix have to match the rows on the second matrix, or you'll get an error. Right? You'll have a number that's multiplied by something that doesn't exist. So the columns have to match the rows. So when they rotate up, every number has something to multiply against. And so if those don't match in the middle, then you get an error. And then the result is the outer 2 numbers. So we end up with row 1, column, row by column on the outside, that's what the result will be. So M3 is going to be a row 1, the rows of column of matrix 1 by the columns of matrix 2. So if I have a 2 by 3 times a 3 by 2, I get a 2 by 2, which was the previous example. And so the columns of M1 must equal the rows of M2. I think I talk about this in the Excel boot camp, but I just wanted to refresh your memory on this one. So this is our matrix multiplication rule. And in Excel, this is what we would use. M mult, matrix 1, comma, matrix 2. Okay. So in terms of our wave functions, we have our wave functions in columns. And to do this matrix multiplication, we need them to be in rows. Well, that would be a real pain to take the wave function and then plot it on columns and have all of these columns taken up by the wave function. So we can use that transpose. That's why I introduced that earlier. So we have this array of all our wave functions. We just take that block and transpose it, and now it flips it sideways. And that's going to be our M1. And then when we multiply it by that block untransposed, that's M2. And in M mult, then we get the integrals of all wave functions times all the other wave functions. So this is it visually. So here we have our wave functions plotted in 2 columns. When we do the transpose of that, it flips it sideways. So this is the transpose part right there. You don't ever see that. It happens inside the formula. You type in this M mult, open parenthesis, you type out transpose, select these wave functions here, close the parenthesis, comma, and then select them again, close parenthesis, control shift enter, and you've got it. Now this is the wave function. I've only got 2, but I've got all combinations of 2 wave functions. I've got wave function 1 times wave function 1. And what is the integral result? It's 1. So can you see the orthonormality? This is the normalization condition. A wave function times itself is equal to 1 squared. So, and then wave function 2 times itself, that's the wave function 2 squared, integrated over all space, it's normalized. So we get a result of 1. So that's the normality piece right there and right here. And the ortho piece is right here on the off diagonals. So I have wave function 1 times wave function 2, and I get 0. And wave function 2 times wave function 1, I get 0. So it's commutative. It doesn't matter which wave function is first and which one's second. And so that's what we mean by the Kronecker delta. It's 1 if n prime equals n, and it's 0 if n prime doesn't equal n. So we can see the Kronecker delta right there in that matrix. That's pretty cool. So this is also why I like the numerical thing, is some of those things like the Kronecker delta, which you see mathematically, are very visual when you see them in the matrix form. You can see anything off the diagonal is 0, and the diagonals are all 1. That means my set of wave functions is normalized and orthogonal. Okay, so then we go to looking solving the Schrodinger equation. Now here we're going to take derivatives. Derivatives is rise over run, so it's the value of the wave function, the change in the value of the wave function, divided by the change in the x increment, okay? And if I'm looking at the wave function, and I want to say, if I'm standing at 0 and I'm plotting the change, so the change here is obviously negative. It went down a certain amount, divided by a positive number, okay? So I'm going to get a negative slope. But if you look at 0, actually, let me erase that. Let's look at this side 3. Okay, I'm at 0 right here on this function. And I look over here, if I go forward and calculate the slope, my slope is positive. You see that? But the slope at 0 is what? What is the slope at 0? So this is the wave function. So the slope, you can take the tangent here at any point, and you can calculate the slope. So if I'm standing at 0, what is the slope of that function at 0? there's three choices: negative, positive, or zero, or infinity, I guess, but it's not four choices. Right? So yeah, if I take a tangent to that wave function at zero, I have a zero slope. So how do I calculate the rise over run? Do I look forward and take the next value, so change in y versus change in x, and plot that at zero? If I do, that's incorrect because the slope at zero is zero. Do I take the backwards derivative? So do I take the one, this difference here, right here, and divide it by this difference? Well, then that's going to be a negative slope, and the slope at zero is not negative. So right here, this is a big deal. We're taking the centered derivatives. So I'm just going to take this. We've got psi and psi, two wave functions here. This is psi prime. So I'm using the mathematical formulation that psi prime is the first derivative of psi. And look at this formula. Okay? So the derivative, so this is the top different, the rise over run, the top over bottom, the change in this wave function divided by the change in x. And look at these little subscripts. X at I plus 1 minus x, minus psi evaluated at x of I minus 1. So here's I. So the slope that I'm going to plot right here at number 1 is this difference. It's this one minus this one, right? It's the wave function evaluated. Actually, it's one column over. So it's this one here minus this one. Do you see how this value is centered between those two numbers? That's what I mean by centered derivatives. It actually takes into account 3 points, okay? And that's the psi of x plus 1 minus the psi of x minus 1. This is the x plus 1. This is the x minus 1. I plus 1, I minus 1. And then divided by x of I plus 1 minus x of I minus 1. Do you see how it's centered? So I'm going forward and taking the difference from the number behind me. Well, because I need numbers behind me, I've got to expand my box beyond the walls of the box. So if you'll notice here, this black box here is actually my box. So this is the length of the box right here, L. But I've gone 2 data points beyond the edge of the box because every time I take a derivative, I lose a row on either end because I'm calculating centered derivatives. So we lose a row for the first derivative and we lose a row for the second derivative. So I've got to expand my formulas beyond the box by 2 rows. And I can do that numerically. There's nothing physical about that. My particle's not going into the wall. I'm just using the wave function's behavior, this sine function, to give me accurate derivatives so that I get accurate integrals and I get accurate energies, etc. If that confuses you, watch this section again. We could do forward derivatives. We could do the next y minus the current y, the next divided by the next x, divided by the current x, but that's going to shift my functions in that direction. I could do behind me or trailing derivatives, and that's going to shift my function back. And I want everything to be centered on 0. So I need to do centered derivatives. I take the next value minus the previous value and plot it on my current position. Okay, a lot of talk on centered derivatives. You can ask your TA also and when you work on the lab. So Then we take the second derivative, we do it again. So centered derivatives for the second derivative. And now we have all of those constants that come out front. And that will give us the accurate energies in kilojoules per mole, okay, right here. So those constants come out front. We put those constants in front of the M mult and in front of the sum product to get accurate energies in kilojoules per mole. And so when I take that wave function times its second derivative times these constants that come out, then I get the energies of these equations. Okay, and so here's I just zoomed into that M-mult equation. It's not in your notes, but it'll be in the video. Okay, so don't panic. You can't write that down. But it's got all of the cell references, including the minus sign, and 8, and pi squared, and L, and so on. And then the M-mult, the transpose, this is psi, this is psi double prime times dx. Okay, so you have all of that in there. Control-Shift-Enter, boom, you've got all 4 integrals. And so when you do that, you have that 2 by 11 matrix times the 11 by 2 matrix, and you get a 2 by 2 matrix, and those are what we call the eigenvalues. So this eigenvector eigenvalue equation, the eigenvalues are the diagonal of the matrix. So whenever you're reading about quantum mechanics in the future, if you go to grad school and so on, they'll constantly talk about diagonal elements of the energy matrix. Diagonal elements, they're doing it numerically, and they're doing it using matrix multiplication, and here you get a chance to see that. So what we calculated analytically, which was E n equals n squared h squared over 8 ml squared, that's the analytical result, okay? But there's no matrix in there. You don't see it. But if you were to plot that by n, you would get these diagonal values. So n equals 2, you would get that value. N equals 3, you would get that value. So that's what we have. Now we could do the same kind of matrix multiplication for the selection rules. Remember, the transition dipole moment has the x-axis in there. So we have 3 functions multiplied by each other. So let's just do this in parts. I've got my wave function, and then I'm just taking x times that wave function and plotting it here. So that x psi is just my wave function times x. So it's just the x-axis times that wave function. And I've plotted it here. So if we look at this, see the blue curve, wave function n equals 2, and I multiply that by the x-axis, okay? I've got a negative number here times a positive number there, so it makes the blue curve negative. You see that? And then I've got a positive value for x here and a negative value for the wave function here. Negative times positive is negative, so I get a negative part of that function there too. So that blue wave function has been perturbed by light. So if we think of x as light coming in and perturbing, an electric field perturbing that wave function, it's made it different. It's changed its symmetry, and now it can be compatible with an upper state wave function. So when I do this integral, I end up with my selection rules. And so here's our M-mult transpose of the wave functions times the x times the wave functions. And look at this. I get 2 to 2 is 0, but 2 to 3 is non-zero. And 3 to 2 is non-zero, but 3 to 3 is 0. So the selection rules pop out of this matrix manipulation. So that's all combinations. And here it is visually. I take the wave functions times x psi columns, those perturbed wave functions, and I get that 2 by 2 matrix. And you can see those selection rules. At least for these 2 states, we can see which ones are allowed. When you get your spreadsheet built, you can go change the quantum numbers. You can go 3 and 4. You can do 1 and 4, 1 and 5. You can see what kind of selection rules are available. This is just zooming in. Here's the M-mult formula for that matrix. And then here's my high resolution or HD version. So these are my 225 integrals, and you can really see the selection rule pattern here. So notice the pattern. 1 to 2 is non-zero. 5 to 4 is non-zero, but 3 to 3 is 0. 6 to 6 is 0. So even the off-diagonal elements, we have delta n equals plus or minus 1. Those are non-zero and large. So those are our fundamentals and hot bands. Then we have the overtones, which are weaker. The plus or minus 5 overtone is very weak. 7 even weaker, but they're still allowed. They're non-zero. So do you see the pattern of those diagonals? Those are all of your selection rules. And then lastly, you get to plot a simulated spectrum. Now it's a single peak, right? You've got two wave functions. So you're going from one wave function to another. And so I just have you calculate the energies using, now these quantum numbers are tied over to the yellow numbers. That's the other thing. In the spreadsheet, these yellow cells are the ones that you get to manipulate. I think I have you calculating the energy. So you're entering the energy equation here. You're taking delta E, and then you're using this equation to get the transition wavelength. And then you're also calculating the Boltzmann factor, and that goes in here. Okay, so you look in the notes for the Boltzmann equation. You may not, if like in quantum state 2, you may not have a lot of population there, so you may need to crank up the temperature. Now in the lab, it asks you what happens at low temperature. Don't go to 0, you'll get an error. So you can go to like 0.1 or 1 Kelvin, and you'll see that the fundamental is still there. But a lot of people said the fundamental disappears at low temperatures, but it doesn't. They went to 0 and got an error. So don't go to 0 with your temperature to give you inaccurate results. So once you have your spectral wavelength and you pick your spectral line width, you get the Gaussian peak shape. And you've simulated your spectrum. So this is from the wave function all the way to the simulated spectrum in a spreadsheet, all on one sheet. And so enjoy it. I mean, you've got a week and a half to play with this, and then we'll have a test over some of the details. Okay? So hang in there. It's a lot. It's like drinking from a fire hose today, so I apologize for that.